Welcome to this second online lecture on the integument system and thermoregulation. In this particular lecture, we are going to focus on behavioral and physiological mechanisms of thermoregulation, more of a physiology lecture. Maybe before we go much into the detail, remember that when you talk about integument system, we are referring to the skin and its appendages or its derivatives, which are basically hair, nails, sweat glands, and sebaceous glands. But that's not the only component of the integument system. The integument system also consists of subcutaneous tissue, the fat, as well as the deep fascia that separate the subcutaneous tissue from the underlying muscles. We also talk about mucocutaneous junction. These are junctions between the skin and mucous membranes that surround body orifices, leading us to more of the alimentary canal, the respiratory system, and the genitourinary tract. And lastly, when you talk about integument system, we're referring to the breast, both male and female. Leading us to skin itself, the key functions of the skin are to protect us from underlying, or let me put it this way, that the skin protects the body from invasion by microorganisms. So it's an immunological function, offering anatomical barrier to infections. It also offers barrier to mechanical damage, that the skin protects the underlying tissues from damage. It helps to do that because of the degree of keratinization, the degree of stratification of cells, also because of the presence of desmosomes. These are bearing junctions between the cells, and also hemidesmosomes, the thing that anchor the epidermis to the dermis. So a number of things that help the skin to be adapted for mechanical abrasion. The skin is also a barrier against chemical injury. If you have some irritants, chemical irritants on the body, the skin will absorb much of that so that you don't affect the deeper tissues. Also, the skin is helpful in thermal insulation, and also just protecting the body against thermal effect, as well as also protecting against the injury by radiation. You know that UV radiation can cause damage to the DNA, and so the melanin within the skin help to protect against that. The skin is a sensory organ because it has a lot of sensory nerve terminals within it, as well as presence of several sensory receptors, like receptors for touch, for pain, and for temperature. And we alluded to some of these receptors in the first part of the lecture, where we talked about these different sensory receptors. Importantly, also, the skin has excretory function because they're able to excrete some waste products from the body, especially excess salt and excess things like urea can also be excreted through skin, through sweat in particular. The main reason why we're having this lecture is because of that function number 4, the thermoregulatory functions of the skin, and we're going to talk much about that, so let me not say much at this point. The skin also has biochemical synthetic functions, in particular being able to metabolize vitamin D. The precursors of vitamin D come from the skin under the effect of UV radiation before it goes to the liver for some intermediate steps and the kidney for final step. The skin also helps to produce some growth factors which help in repair, especially in the skin. Psychosocial communications can also be considered a function of the skin, especially the facial skin, that can change form, and that can represent different type of communications. Now, the lecture on integument system and thermoregulation, I give it in three parts. The first part, we've already talked about it, which focused on microscopic organization of the skin and its appendages. The second part is what we're having right now, focusing on behavioral mechanisms and physiological mechanisms of thermoregulation. The third part is yet to come, which will be on development and congenital anomalies of the skin and its appendages. So this particular lecture is focusing on that number 2, mechanisms of thermoregulation. Before we go deeper into mechanisms of thermoregulation, it is important to know that the temperature of the deep tissues within our body, what we call the core body temperature, usually remains relatively constant. It doesn't change much in as much as the environmental temperature can change a lot. It usually largely lies within 1 degree Fahrenheit or 0.6 degrees Celsius from the normal. That the only time that you have a very big fluctuation from that normal is perhaps when you are sick. You have some febrile illness, or you have fever, so the body temperature changes quite significantly. Otherwise, in normal scenarios, the body temperature doesn't change as much. It is maintained within some narrow limits. The normal body temperature is very necessary for optimal functioning of the enzymes. Remember, enzymes are proteins. And so for them to function optimally, there need to be a normal temperature. If the temperature goes below that one, the enzymes become largely inactivated, so their rate of metabolism goes down. If the temperature rises fast, it might activate the enzymes so fast, so they function extremely fast. But that will also have its own disadvantage. But if you raise that temperature more, it might just destroy the enzymes, because the proteins, it denatures them. And so you kill them, and so you affect metabolism significantly. It can even cause death. That's why it's important to have that optimal body temperature. It's critical, therefore, that the core body temperature is maintained as constant as possible. You know, there's a big challenge there. The environmental temperature, we know, changes tremendously. But even though the environmental temperature changes tremendously, the body aims at ensuring that the core body temperature is relatively constant. Because of this, we can have the temperature which is on the skin. We can call it the shell temperature or the skin temperature. And then there's a core body temperature, which is the internal temperature or the blood temperature. The temperature of the skin may change a lot because the temperature of the skin is subject to the environmental temperature. But that temperature of the skin is not necessarily the core body temperature. And so what the body focuses on much is the core body temperature to ensure that it's within narrow limits. So the skin temperature can change a lot, but the core body temperature should not change a lot. Experiments have shown that when the environmental temperature changes by about 25 to 30 degrees, it only causes 1 degree change in the core body temperature. That's a very efficient mechanism of thermoregulation, that the body has a very efficient way of maintaining body temperature. We have large fluctuations in the environmental temperature, but very small corresponding fluctuation in the core body temperature. The physiological mechanisms for regulating the core body temperature are generally designed to create a balance between the amount of heat that the body produces and the amount of heat that the body loses. So it's a balance between heat production and heat loss. If the body temperature is so high, it means that a lot of heat has been generated. then the body needs to lose that heat a lot. If the body temperature is low, then the body needs to minimize minimize heat loss and measure on heat gain. So it's a balance between heat loss and heat gain mechanisms. With that, I can now give you the learning outcome. The first one will be basically to state the normal body temperature and talk about how this normal body temperature varies in some physiological scenarios. We will then talk about the body's mechanisms of heat gain and the body's mechanisms of heat loss. After that, we'll talk about the various cutaneous mechanisms of thermoregulation. This is why we're having this lecture this time under this cutaneous or rather integument system, so that we can understand the cutaneous mechanisms of thermoregulation. But we'll also talk about generally the three main mechanisms through which the body temperature is usually regulated. We are going to see some three mechanisms, and one of them are the mechanisms initiated by the hypothalamus. That one we'll talk about more in great detail in that objective number 5, and we'll see how hypothalamus contribute or participate in thermoregulation. After that, we will then talk about some pathological alterations of body temperature, and in particular 3 scenarios: heat stroke, fever, and hypothermia are the subject matter of discussion. So let's begin with the first agenda there, the normal body temperature and its physiological variation. The normal body temperature is approximately 37.0 plus minus some 0 point something. Now, we can't have a very strict body temperature for everybody because we see a lot of variation depending on people, depending on geographical location. Generally, we consider anything falling between 36.0 to 37.5 as being normal limits in many geographical locations. Some people may talk about 36.5 to 37.5. So there's a lot of some variation there. You may not get a very standard one that tells you that this is the actual normal, but at least let's understand that it revolves around 37.0. We have some non-normal physiological variation of the core body temperature. One of them is the fact that there is the normal circadian fluctuation of about 0.6 degrees. This is what this statement means. When you wake up in the morning and when you go to sleep in the evening, or your body temperature in the morning and your body temperature in the evening are different. If you make everything else constant, your body temperature in the morning and your body temperature in the evening are different. How are they different? The evening temperature is higher than the morning temperature by 0.6 degrees. That's the normal circadian fluctuation. Why do we have the normal circadian fluctuation? Because during the day, you are more metabolically active, you've been physically active, and so the body has generated more heat. That's why in the evening, the core body temperature is higher than the core body temperature in the morning. That takes into assumption that you are not working at night physically. So you just slept, and then in the morning you woke up, and then during the day you've been active. How about ladies? During ovulation, the time that ladies are ovulating, their body temperature also rises. There are molecular mechanisms why that happens, but the body temperature rises by about 0.5 degrees during ovulation time. So that's also non-physiological variation of the body temperature. Again, still on ladies, the first trimester of pregnancy is also characterized by a rise in the core body temperature by about 0.5. So if your body temperature is usually 36.0, perhaps this time to be 36.5. Or if it has been 36.8, perhaps this time to be 37.23 there. So that's what I mean, that in the first trimester of pregnancy, the body temperature is slightly higher by 0.5. Children also have a higher body temperature, about 0.5 compared to adults. And the reason for this is because they have a high metabolism. So they generate a lot of heat. Lastly, when performing a physical exercise, and that will depend largely on the intensity of the physical exercise, but when performing a physical exercise, the core body temperature can rise with up to 2 to 3 degrees, can go very high when performing a physical exercise because you generate quite an enormous amount of heat from skeletal musculature. So that's the normal body temperature and its normal physiological variations. Now we can talk about the second agenda there. Let's outline the mechanisms that the body uses to gain heat and also to lose heat. Let's start with mechanisms of heat gain. First, understand that the total heat load of the body comes from 2 major sources. It may come from the metabolic processes within the body, but it can also come from the heat that the body has absorbed from the environment. If you go and bask in the sun, you'll absorb some heat from the sun, and definitely that will also contribute to the total heat load of the body. But even if you don't bask, there'll be some heat that's generated from the body through metabolism. So the one for absorbing from the environment is largely dependent on the environmental temperature. But of course, the one generated from within is dependent on the rate of metabolism. Now, let's debate on that one, the one from metabolic processes. Heat is actually a byproduct of cellular metabolism. So for the metabolic activity that goes inside the cells, there's heat as a byproduct. That means what? That as long as you're alive, as long as there's some cells which are alive within you, you'll always be generating heat constantly and continuously, and you cannot stop it. So we always generate heat from metabolism. When the rate at which we are generating heat becomes higher than the rate at which we are losing heat, then definitely that heat will build up in our bodies and the body temperature will definitely rise. And the opposite is also expected to be true, that if you are losing more than what you are gaining, then the body temperature will fall. The amount of heat that the body produces will be dependent on metabolism. But we can look at this metabolism in 2 aspects. There's a basal metabolism that characterizes life at this basic minimum. And then there's that extra metabolism that will be coming into play because of some other factors. So the basal metabolism is the fact that maintains the basal rate of function in the body that maintains life. Then extra metabolism can be due to other things. For example, if there is increased activity within the skeletal muscles, you decide to take a jog or you run or jump or you swim. So there's some activity within skeletal muscle. It will generate more heat from extra metabolism. And usually this one can generate quite an enormous amount of heat depending on the degree or the extent of physical exercise. Sympathetic stimulation is also an important one. Whenever there is sympathetic stimulation, the norepinephrine that is released from nerve terminals is able to activate various tissues for extra metabolism. So very important that the cell metabolizes more under sympathetic stimulation. Remember, sympathetic stimulation is energy consuming. We also have effects of some hormones. The thyroid hormones, this is thyroxine and triiodothyronine. Thyroxine is T4 and triiodothyronine is T3. Those hormones usually increase the metabolism of cells. Again, the adrenal hormones and especially the catecholamines. We're talking about adrenaline and noradrenaline. These hormones also increase metabolism of cells. So whenever we have release of these hormones in the circulation, there'll be increased metabolism. And that means there'll be increased heat being generated in these circumstances. And now remember that enzymes work within particular temperature range, and that if you raise the temperature, you also raise the activity of enzymes. If by any chance that the body temperature is raised for some reason, perhaps even due to the first 3 points we mentioned there, and so the body temperature rises. When the body temperature rises, this will also increase the enzymatic activity. Remember, enzymes depend largely, the operation of the enzymes depend largely also on the body temperature. So when you raise the body temperature a bit, cellular metabolism also increases because of the increase in temperature. And because of that, there'll be more heat also being generated. So that's also important to take note, that there'll be elevation of the cellular metabolism just because you've raised the temperature of the body. We know that for every 1 degree Celsius increase in body temperature, there's a 10% increase in enzymatic activity in the body. And that means that it will increase, again, metabolism. But remember, that's still extra. So these are the mechanisms of heat generation in the body. And what are the mechanisms of heat loss? Understand that when we are not really doing a lot of physical activity using our skeletal muscles, most of the heat generated from the body will come from organs such as liver, heart, brain, kidney, endocrine glands, and still skeletal muscles. When you're not performing physical activity, the skeletal muscles contribute to about 20–30% of the total heat being generated. However, when you're performing physical activity, the total amount of heat being generated from skeletal muscles increased tremendously. It will be quite high. But when you're not performing activity, it also contributes slightly lower. Well, 20–30% is not very low, but if you compare with during exercise, it's actually low. Since the body works optimally when the core temperature is within homeostatic limits, it has to get rid of that heat that is being produced from these organs. It must get rid of that heat. Otherwise, if it continue producing heat and you don't lose the heat, the body temperature will rise. That is why there must be heat loss, because we are saying that as long as we're alive, these organs will be producing heat from metabolism. So again, we must also constantly get rid of that excess heat from metabolism. We notice that these organs are slightly deeper, but the structure that loses this heat from the body is largely from the skin surface. So what must happen is that the heat that has been generated from these deeper organs must be transferred to the skin surface. And what will help us to transfer that heat to the skin surface? The bloodstream. So the heat of metabolism is usually transferred by the bloodstream. The bloodstream is the main agent of transferring heat from deeper organs and tissues to the skin, so that now from the skin, that heat is now lost to the surrounding air or to the surrounding environment. Therefore, that makes us now make this statement that the bloodstream is the main agent of heat exchange between the core body temperature, the temperature within the deep organs, and the shell temperature or the skin temperature, the temperature of the skin around. It will transfer heat from the core temperature to the shell temperature. When the rate of heat loss is greater than heat production, we will lower the heat load of the body, and we'll also lower the body temperature. And that's the aim of heat loss, to lower body temperature. The rate of heat loss from the body is largely determined by two major things, therefore. It will be determined by the rate at which blood transfers the heat from the deep organs, the deep tissues, to the skin. But it will also be determined by the rate at which the skin is able to transfer this heat to the surrounding. So this is what determines heat loss. Generally, we know that heat will flow from a region of higher concentration to a region of lower concentration, if you can use those terms. But basically, heat will move down its gradient. The net flow will be down its gradient. There are four principal mechanisms of heat transfer. There's the radiation transfer. Radiation transfer is the transfer of heat in the form of electromagnetic waves, and the electromagnetic waves here is basically the infrared radiation. So infrared is basically the heat radiation. Remember, this is part of the electromagnetic spectrum. Apart from radiation, we also have transfer of heat through conduction. Transfer of heat through conduction requires that the two objects through which heat is being transferred are in contact with each other. For example, if you sit on a metallic seat, perhaps without clothes, heat will be transferred from your body to that metallic seat, and I'm assuming that that metal is not necessarily hot. So heat will be transferred through conduction. For the radiation one, if you sit in the sun, and so you bask in the sun, the radiation from the sun will enter into your body. But also think about radiation the other way around. If your body is basically having a higher temperature compared to the surrounding environment, you will actually lose heat to the surrounding, again through radiation. So don't think about radiation only from the sun to your body, also think about radiation from yourself to the surrounding. Think about radiation from even the walls to your body, or from your body to the surrounding air. That is still radiation. Conduction requires contact. And when you think about conduction, think about how does the body lose heat to the surrounding air. The air in contact with the skin surface most likely receive the heat through radiation, or rather through conduction, not radiation. The air in contact with the skin surface receives body heat through conduction. But then after the air has received the heat through conduction, that air warms up and moves away from the skin surface, while it's replaced by cooler ones which come. And that is the concept now of convection. So conduction and convection really go very close together in terms of heat loss from the skin surface. Evaporation is an important mechanism of heat loss from the skin surface, largely converting water into vapor. And as that happens, there is latent heat of vaporization that is absorbed from the skin, and that gives a cooling effect on the skin. This is particularly important when we need to lose a lot of heat through sweat, and so that evaporation becomes very key. Okay, so take note of something that generally radiation accounts for a large proportion of the mechanisms of heat transfer. But conduction and convection usually account for about 15 to 20% of heat loss combined, except that this one can be altered significantly if there is a lot of wind or fan on the skin, because this is what happens. Your body loses heat to the air in contact with the skin surface through conduction. The ability of that air to move off from the skin surface will help you to lose more heat, but that air will move from the skin surface through convection currents, now not conduction. So if your body loses heat to the surrounding air, but that air is trapped on the skin surface, the effect of conduction is therefore lost, because now once the trapped air temperature is almost the same as skin temperature, there's no net conduction from there. But if that air that has been warmed up by your skin is taken away by wind through conventional current, the new air that is colder is replaced and conduction will continue to act. And that is why when it's windy, we can lose heat more. Or basically when you sweat and you fan yourself, you lose heat faster than if there is no wind. Having talked about the mechanisms of heat loss and heat gain, we can now explain the various cutaneous mechanisms of thermoregulation. So there are a number of mechanisms on the skin that are geared towards thermoregulation. One of them is the capacity of the skin to cause an insulation. Now, this is not mainly for the skin, but the subcutaneous tissue, the adipose tissue, the fat tissue beneath the skin, usually act as an insulator for the body. This insulation helps to maintain the normal internal temperature of the body. So if the internal temperature is at 37.0 and the environmental temperature is at, let's say, 10 degrees, the insulator tries to protect the internal temperature from the outward temperature so that you don't lose much. Now, usually fat tissue will not transfer heat very fast, and that is why it acts as an insulator. So the more you have a lot of fat on the skin, the more you are able to insulate the internal core temperature from the external environment. And so if you have very little fat on the skin, you'll be expected to be losing a lot of heat to the environment. It is, however, noted, therefore, that if you have a lot of fat on the skin, then it means that the skin temperature, your skin temperature can actually easily approach the surrounding temperature in as much as the inner temperature is actually still at normal because of the insulation. Remember, the insulation is between the skin outside and the internal body organs inside. And so if you have a lot of fat layer, your skin can be really cold, approaching the environmental temperature. Apart from insulation, we also have the mechanism of cutaneous blood flow. Basically, blood flows into the skin. The skin has several cutaneous venous plexuses. So these are vascular channels that receive the capillaries from the skin. So it's a venous plexus. But importantly also, there are also a lot of arteriovenous anastomosis, that arterioles and venules actually connect directly on the skin. These are arteriovenous anastomosis. Very important to note. So this is what happened. The vasculature of the skin changed tremendously in terms of their luminal diameter. They can undergo vasoconstriction and they can undergo vasodilation. They can vasoconstrict to the point of almost stopping blood flow to the skin, almost, and vasodilate tremendously to the level that they can even accommodate up to 30% of cardiac output. Remember, cardiac output is the amount of blood that the heart pumps in 1 minute, and it's usually about 5 liters in 1 minute. So 30% of that can actually go to skin in full dilatation, and that's quite a lot of blood if you think about it. There are many other organs that require this blood, but 30%, a whole 30% goes to the skin. That's quite a lot in full vasodilation. So because of this vasoconstriction and vasodilation mechanism, the skin is able to control heat, because when you have a lot of vasodilation, it means that the heat from the internal organs is now dissipated to the skin, and so it can be easily lost to the environment. But when it's very cold, the blood vessel undergo vasoconstriction so that the heat from the internal organs is not lost through the skin. That's the whole aim. The vascular tone of these cutaneous vessels is usually controlled by the sympathetic division of the autonomic nervous system. So these vessels are supplied by the sympathetic nervous system. If it's very cold, the sympathetic nervous system acts to cause vasoconstriction on these vessels. If it is very hot inside, then the sympathetic division is inhibited, and inhibition of the sympathetic system causes vasodilation. So don't think that it is stimulation of parasympathetic. No, it is inhibition of sympathetic that causes the cutaneous vessels to vasodilate. And then it's the activation of sympathetic that causes the cutaneous blood vessels to vasoconstrict. Vasoconstrict when it's cold, vasodilate when it's warm or hot. The other mechanism of the skin is piloerection. Piloerection is basically the standing of the hair of the skin. This is also caused by sympathetic stimulation, which causes the erector pili muscles to contract. And when the erector pili muscles contract, the hair that they're anchoring stand like the way you can see in this particular guy, which now appears like goosebumps sometimes, as you can see in that region. So what's the aim of hair standing? This upward projection of hair has twofold effects. One is that it will trap a layer of air next to the skin. We call that insulator air, or we can call the private zone of hair within here. So remember, air is trapped between hair next to the skin. Because of trapping of air there, when now heat is lost from the body to that particular air, the air that has been trapped will have similar temperature like that one of skin. And once the air that has been trapped has similar temperature like that of skin, it means therefore that the body can no longer lose a lot of heat through conduction to the trapped air because they have achieved similar temperature. So that's the aim, to lower heat loss through conduction to the surrounding air. But the second aim is this. When you trap air there, now this air cannot move as fast through the conventional currents. So you kind of arrest the air there, make it more static, and so you don't lose it through conventional current. Because if you are to have conventional current there, that air that has been warmed will move away and be replaced by cold air, and you'll have to lose heat through conduction again to the new cold air. So understand those two major aim of piloerection. Because of the trapping and the inhibition of the conventional currents, usually piloerection will tend to then depress conduction heat loss and conventional heat loss. It's a mechanism, therefore, of heat conservation. Piloerection is a mechanism of heat conservation. Okay, the other cutaneous mechanism of thermoregulation is perspiration, basically sweating. So when we sweat and subsequently the sweat evaporates from the skin surface, that becomes a very important mechanism of heat loss, especially when the surrounding temperature of the environment is higher than the body temperature. Think about it. If your body temperature is 37.5, and let's say the surrounding environment is also 40 degrees, it means that actually you cannot lose heat through conduction to the surrounding environment. As a matter of fact, the opposite will happen. You'll be gaining heat. You'll be absorbing heat from the environment. So when the surrounding environment is having high temperature compared to the body, perhaps the only reliable way that you have in terms of this physiological mechanism is to lose heat through evaporation. So it becomes a very vital mechanism of heat loss in those circumstances where conduction heat loss and conventional heat loss is minimized, almost zero. Now, there are two mechanisms or two types of evaporation that lead to heat loss. There's the insensible evaporation. This is the evaporation that will happen all the time. You don't have control over it. There are no physiological mechanisms that regulate because it's part and parcel of life. This will be happening every time. From the skin, there'll be some little evaporation that is always happening because there's some fluid that the skin releases through the sweat glands that will always happen constantly. And this also happens through even lungs as well. The evaporation that happens through this mechanism, which is not seen, is the one we call insensible evaporation. And it usually amounts for about 600 to 700 ml of fluid per day, where the minimum insensible loss is actually considered to be 500 ml per day. This happens every time, every day, irrespective of the environmental temperature. But then there is the sensible evaporation. This is the evaporation that takes place that we can see as sweat. And this is the one that follows stimulation of sweat glands by the sympathetic division of the nervous system. Now, the sympathetic division of the nervous system stimulates sweat glands, but not using adrenergic stimulation or noradrenergic stimulation, but uses cholinergic stimulation. So following cholinergic stimulation by the sympathetic division of the autonomic nervous system, the sweat glands produce more sweat. And that means more liquid, more fluid, more water is released onto the skin surface. When this water evaporates, what happens? It will absorb the latent heat of vaporization, and so it will have a cooling effect on the skin surface. This becomes very important for any body temperature that's above 37.1 degrees. As you can see here, seems like 37.1 degrees is the critical temperature. So above that, the mechanisms of evaporation become higher than the mechanisms of heat production. But below that one, the mechanisms of heat loss through evaporation are quite lower compared to the mechanisms of heat production. Well, the set point temperature for initiating evaporation also varies depending on the body temperature. So when the body temperature is quite low, when the skin temperature is quite low, there's a lot, the set point temperature for initiating evaporation become a bit higher. And that is very intentional so that you don't lose the heat. But when the skin temperature is quite high, the set point temperature for initiating evaporation is also quite low, so you lose more heat through evaporation. Now we can talk about the three main mechanisms through which body temperature can be regulated. They are simple. One is basically what we call the voluntary behavioral mechanisms. The second one are the local skill temperature reflexes, and the third one, hypothalamic mechanisms. I want to explain each of them. Let's begin with the voluntary behavioral mechanisms. When you talk about voluntary behavioral mechanisms of thermoregulation, we're just referring to the behavioral modifications that we as human beings undertake to either prevent overcooling or overheating our bodies. So what is it that you usually do as a choice that you make to prevent your body from perhaps overcooling or overheating? Let's start with a scenario where it's very cold, so you don't want to overcool your body. What do you usually do? A number of things you can do or you've done. Perhaps you can choose to just make some hot coffee and drink, and that will help you, by the way. You can also decide to just put on even a sweater or a jacket, something warm, to just make your temperature be better. You may decide to just bask in the sun, or if you can afford, you just make a fireplace and you just warm yourself. You may also decide to just take a run or some jogging. Just do some physical exercise and generate heat from yourself. Or you can decide to clinch, make a clinch of yourself so that you reduce this part of the body. And sometimes this happens so subconsciously, you don't even know that you've taken a particular posture when it's very cold. How about when it's very hot? What is it that you do? You can decide to take a swim. Well, maybe very few will do that, but it's a mechanism. Or you can decide to take a cold shower. You can decide to take cold drinks. You can decide to remove some clothing, hope not everything. You can also decide to use a fan or air conditioner, depending on where you are. You can decide to just go under a shade or maybe in a cooler place. You can decide to take a rest, basically reducing the physical activity. So these are behavioral mechanisms that we take. They're just modifications we consciously do from our voluntary choices to adjust our body temperature. There's some places where this becomes very key, especially if you are in the temperate climates. This becomes very, very vital. The other physiological mechanisms may not operate fully. If you're in a very icy place and you're just with a t-shirt, you will still suffer. But if you can dress warmly, you will significantly help the other physiological mechanisms. Okay, second major mechanism is the local skin temperature reflexes. So these are basically physiological cutaneous adjustments that occur on limited regions of the skin, in which case that particular region of the skin has been exposed to a different temperature from the one that is being exposed to the whole of the general skin. Take, for example, that it's a hot day, fine, but you've just dropped a cube of ice on the dorsum of your hand. So we can't say because of that single cube of ice that now your body temperature has fallen, not quite. But definitely the temperature of the place where that cube of ice is on your skin has definitely gone down. So there need to be some mechanism that sort of that particular small area rather than just adjusting the whole of your body temperature. Similarly, if you sit on a very warm thing, or you put a warm thing on your hand or on your skin, that particular region in contact with that warm thing will have an elevated temperature, definitely. And so there needs to be mechanisms of sorting that particular small region. So these ones are caused by local effects of temperature, which are direct on the blood vessels. If there is a warm thing onto your skin, it will cause vasodilation directly. And if it's a very cold thing on your skin, it will cause vasoconstriction directly. But other than that, there's some reflexes which are conducted from the skin to the spinal cord and back to the skin area as well as the sweat glands around. So for example, if it's a hot thing that is in contact with your skin, there'll be a reflex to the spinal cord segment and then back to the sweat glands around there that will cause the sweat glands around there to open up a bit and be stimulated so that these sweat glands will then produce some more sweat, not necessarily profusely the whole body, but that region can actually increase the amount of sweat secretion. Similarly, if it's cold, they'll be inhibited. So these are the local skin temperature reflexes. They only affect a localized area. They involve localized cutaneous vasodilation and vasoconstriction. They also involve localized or mild increase or reduction in sweating, depending on the scenario. The third major mechanism of thermoregulation are the hypothalamic mechanisms of thermoregulation. And so that brings me to the fifth agenda of this talk. Let's talk about the body temperature regulation by hypothalamic mechanisms. We know that the body temperature is regulated by neuronal feedback, which are mediated by the hypothalamus, and this becomes very central in thermoregulation. The mechanisms operate by being controlled from the hypothalamic center, which we call the thermoregulatory center, located largely in the posterior hypothalamic area. So the thermoregulatory center is located within the posterior hypothalamic area. But this center relies on input that it receives from thermoreceptors. These thermoreceptors can be peripheral thermoreceptors, where most of them are actually from the skin, although some of them could be in some blood vessels, like some veins, some large veins within the abdomen and the like, or some of them within the spinal cord itself. They're still considered peripheral thermoreceptors, but most of them are on the skin. So the ones on the skin will carry shell temperature, the skin temperature. We have central thermoreceptors. The central thermoreceptors are located largely in the anterior region of the hypothalamus, the anterior hypothalamic area. That's the region of the preoptic nucleus. That region has the central thermoreceptors which detect the temperature of blood. And so that is the core temperature that is detected by the hypothalamus. So the regulatory center within the hypothalamus relies on information from the skin and information from the hypothalamus itself regarding the body temperature. What does it do with that information? The thermoregulatory center of the hypothalamus will regulate the body temperature around 37.0, 37.1. That is the one that is termed the hypothalamic set point temperature. Now, this is what that means. That the hypothalamus has set a particular temperature within it, above which it will understand that it's too hot, and below which it will understand that it's cold. And so if the body temperature falls above 37.1, then hypothalamus will have the understanding that now the mechanisms of heat gain are exceeding heat loss. So it should reverse that so that the body temperature goes down. Similarly, if the body temperature falls below 37.0, hypothalamus will understand that now we're in a cold war. So we need to increase mechanisms of heat generation and perhaps minimize the mechanisms of heat loss so that we can restore the body temperature. The set point temperature becomes a reference point for the hypothalamus, around which it will now be regulating the body temperature. So if for whatever reason the temperature is high or low, the hypothalamus will initiate some reflexes that will appropriately restore the body temperature. These reflexes will primarily target the following tissues. It will target the cutaneous blood vessels that we've mentioned. So they will either undergo vasoconstriction or vasodilation. And remember, this is dependent on sympathetic activity. Vasoconstriction is caused by increased sympathetic stimulation, and vasodilation is caused by inhibition of sympathetic stimulation. It will also target sweat glands. Again, this is still cholinergic sympathetic stimulation, causing increased sweating, and inhibition of sympathetic stimulation causes reduced sweat production. It will also target erector pili muscle. Again, this is also targeted by the sympathetic stimulation that causes this erector pili muscles to contract, and this causes piloerection. And if there is no sympathetic stimulation, then the muscle is relaxed and the hair falls. The other target tissue would be the skeletal musculature. Maybe not directly. Basically, what hypothalamus will do is to increase the tone within the skeletal musculature. And because of that increased tone, the reflexes between the spinal cord and the muscles will then cause some shivering mechanism when it's cold, and lack of it when it's not cold. Lastly, the other targets are the adrenal and thyroid glands. In particular, the thyroid glands will be activated from, hypothalamus produces what we call thyrotropin releasing hormone, which then acts on the anterior pituitary gland to produce a thyroid stimulating hormone. Then from thyroid stimulating hormone of the anterior pituitary, it will act on the thyroid gland to produce thyroxine and triiodothyronine in T4 and T3. These hormones increase metabolism of cells. For the adrenal gland, the hypothalamus, through the sympathetic outflow from the hypothalamus, will then go to the sympathetic nerves that go to the adrenal gland, and in particular the adrenal medulla, causing production of catecholamines. Catecholamines will also increase metabolism of cells. So these are the target organs or tissues which are utilized by hypothalamic mechanisms to restore body temperature. We need to understand this model before I give you some scenarios. So this is what we've said, that we have thermoreceptors in the body. These thermoreceptors can be detecting the temperature of skin. We've called them peripheral thermoreceptors. But these thermoreceptors can also be detecting the temperature of blood. We call them central thermoreceptors. In particular, the central thermoreceptors are located within the anterior hypothalamic region around the preoptic nucleus. Information from either peripheral thermoreceptors or central thermoreceptors is directed to the thermoregulatory center, again within the hypothalamus, and this is now within the posterior hypothalamic region. This thermoregulatory center of the hypothalamus initiates mechanisms that restore body temperature depending on the direction we are. And these mechanisms target some 5 regions: cutaneous blood vessels, erector pili muscles, sweat glands, skeletal musculature, and some endocrine glands, in particular adrenal and thyroid glands. So that's the model we've described. Hypothalamus is able, therefore, to maintain the body temperature at a constant despite a lot of oscillations in the atmospheric temperature. The body temperature is maintained at relatively constant over a very wide range. Remember also what I told you about its ability to initiate sweating when the body temperature is quite high. The set point temperature for evaporation become a bit low, so that heat loss is facilitated easily. But when the body temperature is quite low, the skin temperature is quite low, the threshold for initiating sweating is also quite high. You don't necessarily lose the heat. Let's take some scenario. Let's consider that the body temperature is very low, or rather, the surrounding temperature is low. How does hypothalamus help us to respond to cold scenario? Hypothalamus will initiate twofold responses to cold. One will be responses that initiate mechanisms of heat conservation. That little heat that is already inside the body, please don't lose it. That is what hypothalamus will do. It will ensure that the heat that is inside the body, you don't lose as much. So it will initiate mechanisms of heat conservation. These mechanisms of heat conservation largely target the cutaneous structures. But then it will also initiate mechanisms that help us to produce more heat, the extra metabolism we talked about. These ones will target largely the skeletal muscles and the endocrine glands. So if we're to put that in perspective, in response to cold, hypothalamus initiates mechanisms of heat conservation, as well as mechanisms of heat gain, mechanisms of thermogenesis. The mechanisms of heat conservation revolve around 3 target tissues. For the blood vessels, they undergo vasoconstriction and a sympathetic stimulation, so you don't lose a lot of heat through skin. They'll also target the erector pili muscle. There'll be piloerection, so you trap air next to the skin. You don't lose it through conduction. You don't lose heat through conduction much. And then we also target sweat glands. In this case, there'll be inhibition of sympathetic innervation to sweat glands. Hence, there'll be reduced sweating. These are the mechanisms of heat conservation that the hypothalamus initiates. But hypothalamus will also initiate mechanisms of thermogenesis, particularly targeting skeletal musculature, where the muscular tone is increased, and so the reflex of the spinal cord causes shivering, affecting the antagonistic muscles. It will also target the adrenal and thyroid gland, which produce their hormones, so catecholamines and T3, T4 hormone. And these ones will increase metabolic rate of various tissues. So these ones will increase heat generation. These ones will increase, or rather will reduce heat loss. Okay, we can take another scenario. How about response to heat? Again, hypothalamus initiates some twofold responses. If it is too hot, and hypothalamus will initiate mechanisms that promote heat loss, again targeting cutaneous structures, and mechanisms that minimize heat production. Take note that we cannot stop heat production as long as we're alive, but you can minimize heat production. So in response to higher temperatures, the mechanisms that promote heat loss will be targeting cutaneous structures. For blood vessels, there'll be increased blood flow because of vasodilation. This is due to inhibition of sympathetic stimulation to these blood vessels, causing vasodilation. Therefore, there is increased dissipation of heat to the cutaneous structures with subsequent ease of heat loss to the surrounding. There'll be relaxation of the erector pili muscle. That means that the hair falls. And there'll be increased sweating following sympathetic stimulation of the sweat glands. And this, remember, is cholinergic stimulation, causing the sweat glands to increase in producing sweat profusely. And so we lose heat. And so that means there'll be a cooling effect through evaporation. These are mechanisms that promote heat loss. The mechanisms that minimize heat gain will be basically reducing the tone of the musculature. And so there'll be inhibition of shivering. And also there'll be less production of hormone from these two glands. And that means that the metabolism will not be raised as such. There'll be no extra metabolism. These are the mechanisms initiated by the hypothalamus to respond to higher temperatures. We can now finish our story of thermoregulation by talking about some pathological conditions revolving around thermoregulation. I'll start with pathophysiology of heat stroke. Now, the response to high temperature is a spectrum in terms of abnormalities. The extreme of that spectrum is heat stroke. But before you get to heat stroke, you can also get heat exhaustion and the like. But I'll discuss heat stroke. So heat stroke is heat-related illness and is defined as the body temperature that is quite high associated with neurological dysfunction. So you find that the body temperature has gone so high and there is associated neurological dysfunction because of that. Let's explain it this way. Heat stroke will commonly happen when the environmental temperature is high and there's also a lot of humidity. Now, why humidity? If there's no humidity, the ability to lose heat through evaporation is quite efficient. If the air is dry, the evaporation mechanism from the skin is quite efficient. So you sweat, you lose that heat quite fast. However, when the humidity is high, the mechanisms of heat loss become very ineffective. Remember, the air is hot, so you can't lose heat through conduction from the body to the surrounding. Neither can you lose through convection. So you're only relying on evaporation. Now we are saying, even for that evaporation, the air is also humid. So the rate of evaporation is quite reduced, almost ineffective. So what happens? It means that the body cannot lose heat effectively. So think about if this person was physically active, doing something, or even not doing, the body temperature will continue to rise because the mechanisms of heat loss are ineffective. And so the body, total heat in the body will continue to build up, causing the body temperature to rise. When the core body temperature rises to about 41 degrees, that's really high. A core body temperature of about 41 degrees or even more shuts down the neurons, including the thermoregulatory center of the brain is shut down so that it can no longer function properly. And that's the story. That if the thermoregulatory center of the hypothalamus is depressed, it can no longer control thermoregulation. It can no longer control the heat mechanisms. So what happened? It will not initiate mechanisms of heat loss anymore. It has been suspended. So the body continue to generate more heat still. And the more heat is generated, the more the body temperature rises, the more hypothalamus is depressed, the more it cannot initiate mechanisms of heat loss, the more heat is generated again, the more temperature rises. It becomes a very terrible positive feedback vicious cycle. Not so good. The rising temperatures will increase metabolic rate, which means that the enzymes within the body will also continue to catalyze even faster. And so this one also causes the temperature to continue rising. Heat production basically rises in a vicious manner. When the temperatures become so high, the proteins are denatured, enzymes are denatured, neurons are destroyed. Some children may actually get convulsions, and it can actually lead to death as well. So this is basically heat stroke. Now, the main difference between heat stroke and perhaps heat exhaustion is that in heat exhaustion, the hypothalamic thermoregulatory center is still functioning. But in heat exhaustion, you find that perhaps somebody has sweated a lot until they become dehydrated, or they have lost a lot of salt through the profuse sweating. So they also perhaps collapse. The body temperature is quite high and they collapse, and then that's what we call heat exhaustion. In heat stroke is the extreme of heat-related illness, in which case the thermoregulatory center is actually depressed. So it's not functioning. Let's compare that with the fever. So what's fever? In fever, the body temperature is elevated, although the patient or the concerned person is complaining of cold. And in most cases, this scenario is in a situation where there is an infection or some molecules that adjust the hypothalamic set point temperature. So it's about adjusting the hypothalamic set point temperature upwards. Let's consider this scenario for us to understand. Let's take that vertical graph to be the temperature curve, and this horizontal graph to represent time in hours. Under a normal scenario, the set point temperature within the hypothalamus is about 37.0 or 37.1. So your body temperature will be revolving around 37.0, 37.1. So over time, the hypothalamus ensures that your body temperature, the actual body temperature, the elongated dots is revolving around that one. And that's considered normal. Somebody may get an infection, and these infections that adjust the hypothalamic set point temperature are called pyrogenic infections. Through this infection, there are some molecules which are released in the circulation. They are inflammatory molecules like interleukin-1, which have the capacity to elevate the hypothalamic set point temperature. So consider this. The normal set point temperature in the hypothalamus is 37.0. But you get an infection that resets the hypothalamic set point temperature, and we can take a scenario. It has now reset this one to 40 degrees. What happens? Even though the actual body temperature is 37.0, as long as the hypothalamic set point temperature is higher than that, the hypothalamus will tell the body that it is very cold. And so what will happen thereafter is that hypothalamus will initiate mechanisms that help that actual body temperature to reach the new set point temperature, even if it's abnormal. This journey from here to there to the new abnormal set point temperature will be characterized by the patient feeling very cold. The patient will be perhaps putting a lot of blanket on them or sitting next to fireplace. It will also be characterized by mechanisms of heat conservation and mechanisms of heat gain. This is the time that the patient complains that they're feeling very cold. It's also the time that the patient will be having a lot of shivering. We call it the chills stage of fever. So this chill stage of fever is characterized by mechanisms of heat conservation and mechanisms of thermogenesis, characterizing that part. And as long as the actual body temperature is still below the new set point temperature, things will go on and the chills will go on until the new set point temperature is achieved. It doesn't have to be 40. I've just used 40 for illustration. When the actual body temperature hits the abnormal one, now the person will be feeling normal. Although if you take their body temperature, you'll think they're really burning. But they'll be feeling normal now. So normal mechanisms operate there. Well, that will sustain as long as nothing interrupts, nothing reset by the set point temperature. Occasionally, what we do as clinicians is that we administer some drug, paracetamol or aspirin. What these drugs do is to reset the set point temperature. So in this case, it was at 40 degrees. It will now reset it to the normal one, which is 37.0. Immediately that happens, guess what the patient feels? They are burning because the actual body temperature is now 40 degrees C, but the new set point temperature has now been to 37.0, what it was originally. So this person will be feeling like their body is definitely burning. The normal set point temperature is 37.0 in the hypothalamus. The actual body temperature is 40. So what will happen? Hypothalamus will initiate mechanisms of heat loss actively, and will also initiate mechanisms that inhibit heat gain. This stage of fever is characterized by a lot of sweating. And this is what we call the crisis stage of fever. If you notice, whenever somebody takes paracetamol, if they have fever, they'll almost always have some sweating that follows that drug. That's basically what happens. The drug has now reset the temperature to normal. And so the body temperature is now being lowered to that one, then the crisis stage of fever. So basically, that is the pathophysiology of fever. Now let's talk about hypothermia. Hypothermia is a low body temperature resulting from prolonged and controlled exposure to cold. If you expose yourself to cold for a long period of time, you get low body temperature, and we call that hypothermia. Good news is that most body tissue can actually withstand marked reduction in body temperature as opposed to marked elevation of body temperature. From 37.0, if you go to 43, you actually destroy cells so much, can cause death. But from 37.0, you can lower to near 30, and most body tissues are still withstanding it. Now, extreme cold has some effects on the enzymes. When it is extremely cold, the cellular enzymes become now lazy. They don't operate optimally. And so because of that, it will lower some vital functions. For example, the rate at which you breathe will be going down. Blood pressure will fall because now muscles are not contracted as much, the smooth muscles. The heart will not be beating as strong because of that as well. You remember that you are cold, so you are shivering, but if you reduce these ones and the enzymes are also reduced, even the shivering will stop at some point. Usually shivering tends to stop when the body temperature is about 30 to 32 degrees. And especially at this time, now the body has exhausted its capacity for generating, because now the enzymes are now sluggish, they're weak. And remember, we're relying on metabolism. So if you can't have that metabolism, shivering stops. In most cases, drowsiness will set in. Oddly enough, the person will now start feeling comfortable, even though previously they felt extremely cold. Now, the reason why they'll be feeling comfortable is because now you've inhibited those mechanisms of trying to generate heat. They're now not functioning, and that's why they're feeling a bit comfortable. But that doesn't mean good. It's actually a bad sign. It can progress to coma and even death, and death usually ensues because of cardiac arrest. The heart goes into a stop, especially when the temperature now approaches 21 degrees C. Great, that is hypothermia. And that brings us to the end of this second lecture on integument system and thermoregulation, where we've looked at mechanisms of thermoregulation, both behavioral and physiological mechanisms of thermoregulation. The third part of this lecture on integument system and thermoregulation will be on development and congenital anomalies of skin and its appendages. Thank you very much.